Okay, so welcome back to what is going to be the last section we're going to be talking about. Section 5.5 called the Substitution Rule. Or if you took calculus in high school, you might recognize this concept as U-sub. Okay, so far, what have we done in this chapter? Well, we've had things like, let's take the function 4 minus 2x and look at the area bounded between the curve from 2 and 5. So that's something like 2 and 5, so that's going to be there's some negative area there. So we're looking at this area. And before, we were doing things like, okay, you could approximate it, right, by rectangles. It's when you're starting to draw these things. Rectangles, and you're filling them in. And you could do those computations. Then we said, okay, let's look at Riemann sums. Let's just look at the sum and take it as n goes to infinity. What does that give us? That was what the definition of what an integral, what this notation means. And then we said, well, that's all fine, but there's this thing called the Fundamental Theorem of Calculus that lets us do it a lot faster using antiderivatives. And for a problem like the one above, that one's pretty straightforward. What do we get? Well, you have to, an antiderivative for this one would be 4x minus x squared, and you have to evaluate it at 5 and then subtract valuing it at 2. So that would be 20 minus 25 minus, plugging in 2, 8 minus 4, which will give you a number. Okay, so that's where we are as of now. But there are other rules that we can sort of look at to see different types of integrals that maybe we don't just straight out know the antiderivative for just by looking at it. So I'm going to use an indefinite integral to start out. Let's suppose we have this function. How would I integrate that? Well, first thing I notice is at this point in time, I don't just have a polynomial yet, I have this term squared and then multiplied by an x. So I really can't do anything as a power rule yet. But what I can do is I can expand this, so x to the 4th minus 4x squared plus 4 dx, and distribute everything. And take the antiderivative using the power rule. Two x squared plus c, because this is an indefinite integral. And that's all fine. But is there a quicker way? Like, what if I change this as something to the 5th? I really don't want to do that integral if I don't have to. And there is a quicker way. And it is analogous to how we had the chain rule for differentiation. Now we're going to have the substitution rule for integration. The idea is Well, let's do a change of variables. Because we can't just straight out integrate it as is. Let's change the variables. So for my change of variables, I have a couple options. So this is going to be sort of like chain rule. So you want to think, what's my innermost thing? I'll say x squared minus 2. What would happen if I then substitute that? Well, I still have an x, but then I have u to the 5th dx. But that's a little bit of a problem for the substitution rule so far. Look, I have a u, but I still have a dx, so I'm integrating, and there's an x, taking x to be my variable. So that's a little bit of a problem. But what I can do is I can say, well, I had dx before. What about du? Can I somehow write a du? Well, you could take the derivative with respect to x of u. You'll get 2x. And we can think about this as, well, let's just solve for du. Du is 2x dx. So if we had 2x dx, we could substitute. Another way of thinking about this too is we could solve for dx, and what do we get? We get dx is du over 2u, or 2x. So what does that give us? Well, now we can substitute in dx, and we get du over 2x times u to the 5th, or simplified, that would be u to the 5th du. Okay, so now that's something we can integrate. Notice that my differential, or this d something, when I have the u, du, that u matches the variable. So I can integrate this thing. It's going to be u to the 6th over 6 plus c. But I had already said what u was. It's x squared minus 2. So I can substitute this and get a final answer. If I looked at this more complicated one where it's to the 5th instead of squared, I'm going to get 1/6 x squared minus 2 to the 6th power plus c. And that's the substitution rule, is let's use a change of variables, and the fact that du equals 2x dx to find out what this integral is. Like I said, it's the chain rule for integration. So let's just do a couple examples. We're going to stick with the indefinite integral for this video. Next video we'll talk about what happens when you go to a definite integral. Okay, so this example, e to the 5x dx. Well, I want to think, I'm going to tell you this is going to be a u sub, or a substitution rule. So I want to think what my u is going to be. Now remember, I know the integral of e to the x dx, but I don't know the integral of e to the 5x dx. So why don't I make my u be 5x? Take the derivative, and what do I get? 5. And then, so if I solve for dx, I get dx is going to be what? Du over 5. And you can get that, multiply dx to both sides, divide by 5. Okay, so let's go back to this integral. It's going to be e to the u, and then times du over 5. Constants pull out of integrals. This is e to the u du, or 1/5 e to the u plus c. And then remember, at the end of these, always substitute back the u if it's an indefinite integral. You'll get 1/5 e to the 5x plus c. And that's how these ones work. They're called u subs. Okay, so let's do another example. Let's do some trig. Cosine cubed theta, sine theta, d theta. Well, I will say first of all, because I have these two things being multiplied and we haven't talked about a sort of product rule yet, and we're not going to in this course. This is a perfect candidate for substitution rule. So, I want to think, what are the potential things I have that I can make my u? Or, this time I won't call it u, I'll call it, let's call it y. What can I make my y? Well, I have a sine theta, right? I could try sine theta. So then my dy d theta is cosine theta. So d theta is going to be dy over cosine theta. I could substitute times y times dy over cosine theta. But you're going to see a problem just in a second. What is this going to give us? It's going to give us cosine squared theta y dy. But now we have two variables. So when you have two variables, and you've already substituted in for the differential, that d something term, that's usually a good sign that maybe if you're doing substitution rule, maybe you should choose something else to substitute. So sine didn't work. Let's try cosine theta. So dy d theta, take the derivative, negative sine theta. That means that d theta, if we solve, will be negative dy over sine theta. Substitute this one in. Cosine cubed theta is going to be cosine theta quantity cubed, so this is y cubed. And then sine theta, substitute in for d theta, you get negative dy over sine theta. So this is going to be negative, you can pull the negative out, y cubed dy, and you can integrate that. That's negative y to the 4th over 4 plus c, or substitute back in, negative 1/4 cosine to the 4th theta plus c. Right, so the steps is identify what you're substituting in, take the derivative, solve for whatever is over here, that is the d theta in this case, substitute all that in, cancel, and take the integral. Okay, so let's do one more example. y squared times the quantity 4 minus y cubed, all raised to the 2/3 dy. Okay, so why don't you pause the video and do this particular example first. Okay, so I hope you did that example. Well, I'm going to call x my new variable. I have a couple options. I could choose y squared. I could choose 4 minus y cubed. But I noticed that there's this 2/3 power here. So the inside might be, thinking about it in terms of sort of chain rule like, the inside is probably what my substitution is going to be. So then you take the derivative. What do you get? Negative 3y squared. You solve for our differential, dy. You get dx over negative 3y squared. You can plug this in. Still have a y squared, but then the inside becomes x to the 2/3, and my dy becomes dx over negative 3y squared. This is all multiplication, so the y squareds cancel, and we're left with the integral of negative x to the 2/3 over 3 dx. So the negative 1/3 pulls through. You integrate x to the 2/3 dx. That's going to be, you add 1 first, and then you divide by the new exponent. But this dividing by a fraction is the same as multiplying by the reciprocal. So you have to multiply by 3/5 to negative 1/3, and you'll get negative 1/5 x to the 5/3 plus c. And we're almost done. Remember, x is not our original variable, so we need to plug it in. And then we're done. No simplification needed. Okay, so tomorrow we will continue this, going over how does this apply to definite integrals, and finishing up that section. So I will see you all then.